Imagine a bird that can hear a mouse's soft sigh from 300 feet away, even as midnight wind rattles the forest. That bird is the owl, and its secret weapon isn't its eyes but a delicate, cup-shaped crown of feathers called the facial disc. Those feathers act like a living satellite dish, gathering sound waves and funneling them straight into the owl's ears with a precision that would outclass the best human engineers. When an owl glides silently over a meadow, it can pinpoint the tiniest rustle of a beetle's wing and lock onto that source as if the night were a perfectly still pond. Researchers have measured the acoustic gain to be roughly 10 times louder than the raw sound, a boost no powered device can match without electricity. The efficiency of this natural sound collector lets owls hunt in total darkness, relying on acoustics where vision fails. So the next time a hoot drifts through the trees, remember you are hearing a masterpiece of evolutionary engineering, a quiet miracle that turns silence into a sonar map of the night. In the hush of temperate forests, boreal woodlands, and even arid scrub, owls hold court after the sun sinks. Their round heads swivel like silent sentinels, eyes fixed forward while the world around them becomes a sea of darkness. The facial disc, a shallow bowl of stiff feathers surrounding each eye, varies in size from the tiny elf owl to the massive eagle owl, but all share the same purpose: to capture and direct sound. These birds perch on gnarled branches, on the edge of open clearings, or on the low limbs of ancient pines, awaiting the faintest movement below. The environment they choose, deep understory, moonlit fields, or mist-cloaked wetlands, creates a natural acoustic chamber where every whisper is amplified. Nighttime temperatures cool, air becomes denser, and sound travels farther, granting the owl an auditory reach that rivals submarines in the deep. Their talons, sharp as needles, remain poised, ready to strike the moment the acoustic map points to prey. Understanding the owl's habitat is the first step toward appreciating how evolution sculpted a creature that lives by hearing more than by sight. The science of owl hearing began with simple observations: two ear openings placed at different heights, a facial disc that seemed too perfect to be accidental. Modern researchers have confirmed that the disc functions like a parabolic reflector, gathering sound waves and focusing them onto the ear canals. Inside each ear, the owl has an asymmetric bone structure that creates a timing difference of just a few microseconds between the left and right sides, allowing it to calculate the exact vertical and horizontal position of a sound source. High-speed video of captive owls swiveling their heads shows them turning only a few degrees while still locating prey, proof that the facial disc does most of the work. Acoustic experiments in anechoic chambers reveal that an owl can detect frequencies as low as 20 Hz and as high as 12 kHz, a range broader than most mammals. Moreover, the feathers of the disc are arranged in concentric rings that can be individually adjusted, fine-tuning the acoustic focus much like a camera lens changes focus. All these findings paint a picture of a bird that has turned the physics of sound into its most trusted hunting tool. One of the most astonishing discoveries came when researchers placed tiny microphones beneath a blanket of fresh snow and played the faint rustle of a beetle moving above. The owls, perched a few meters away, instantly adjusted their flight path, zeroing in on a target that was entirely invisible and muffled by insulation. This means the facial disc can capture vibrations that travel through solid media, not just through air. Even more surprising, the owl's ears are tuned to detect the minute difference between sounds that have been reflected off the snow's surface versus those that pass straight through, allowing it to gauge depth as precisely as a sonar ping. In controlled tests, an owl could locate a hidden mouse under 10 centimeters of compacted snow with an accuracy of less than half a centimeter. Such performance was once thought impossible for a creature without any echolocation organ. The discovery reshaped our understanding of avian hearing, showing that owls have evolved a hybrid acoustic system that works in both air and solid substrates, turning winter's white blanket into a transparent map of life below. To appreciate how the facial disc works, picture a concert hall whose walls are covered in soft, angled panels that guide every note toward the orchestra. The owl's feathers are arranged in concentric arches, each one slightly angled inward, forming a three-dimensional funnel. When a sound wave strikes the outer rim, it is gently redirected toward the inner rings, losing energy but gaining directionality. The central depression, known as the facial ruff, acts like the throat of a trumpet, concentrating the pressure of the wave onto the ear openings. Experiments using laser vibrometry have shown that the outer feathers vibrate at lower frequencies, while the inner feathers resonate with higher pitches, effectively separating the sound spectrum much like a graphic equalizer. This dual-layer system allows the owl to amplify quiet, low-frequency rustles while simultaneously sharpening the crisp, high-frequency clicks of insect wings. Moreover, the owl can subtly adjust the tension of these feathers by altering muscle tone around the skull, fine-tuning the focus depending on distance and ambient noise. In essence, the facial disc behaves as a living acoustic lens, dynamically reshaping the acoustic field to give the owl a crystal-clear picture of its shadowy world. The true turning point in our story arrives when we realize that the owl's acoustic abilities are not limited to hunting alone. They also shape its entire nocturnal existence. While most predators rely on sight to patrol territories, owls use their facial disc to map the soundscape around them, creating a three-dimensional sonar-like map of every rustle, wind whisper, and distant waterfall. In dense forests, an owl can detect the flutter of a moth's wing hundreds of meters away, even if the insect is hidden behind a curtain of leaves. This ability allows the bird to avoid rivals, locate mates, and even gauge the size of an approaching storm, all without ever opening its eyes. One study recorded an owl navigating a labyrinth of branches in complete darkness, relying solely on the subtle changes in echo and frequency that its own facial disc amplified. The bird's head remained still, yet its auditory map guided it through narrow gaps with the precision of a human pilot using instruments. This shift from a simple hunting tool to a full-fledged sensory radar transforms the owl from a nocturnal hunter into a master of night, turning darkness into a canvas it can read and paint upon. The implications of the owl's acoustic mastery ripple far beyond a single species. If a bird can turn a simple feather arrangement into a high-resolution sonar, then the evolutionary pathways that lead to such innovations are more diverse than previously imagined. It suggests that natural selection can sculpt sensory organs from structures that were originally meant for entirely different purposes. Feathers for insulation become sophisticated acoustic lenses. This challenges the long-held belief that complex sensory systems, like echolocation in bats or dolphins, must evolve from dedicated organs. Moreover, the physics uncovered in the owl's facial disc inspires engineers to design passive acoustic devices that require no power, mimicking the bird's ability to focus sound using only shape and material. Some researchers are already prototyping wind turbine blades and underwater microphones that echo the owl's feather geometry, hoping to create quieter, more efficient technologies. In the broader picture, the owl reminds us that nature often finds elegant, low-energy solutions to problems we deem difficult, urging us to look closely at the quiet corners of the world for the next breakthrough. Human beings have long been fascinated by the owl's uncanny hearing, weaving it into myths, symbols, and practical applications. In ancient Greek lore, Athena's owl represented wisdom, a creature that could see what others could not, an early acknowledgement of its superior perception. Indigenous peoples of North America have told stories of owls as night watchmen, guiding travelers through darkness with their keen ears. In modern times, engineers have turned to the owl's facial disc for inspiration, developing acoustic sensors for autonomous drones that navigate by sound in cluttered environments. The medical field, too, has borrowed principles from the owl's ear asymmetry to improve directional hearing aids, allowing users to pinpoint sounds in noisy settings. Even artists have captured the eerie beauty of an owl perched against a moonlit backdrop, using its image to evoke mystery and insight. This deep cultural resonance shows that the owl's extraordinary hearing is not just a biological curiosity. It resonates with our own desire to listen more deeply, to understand the unseen, and to harness nature's designs for our benefit. Despite decades of study, many questions about the owl's acoustic system linger like whispers in the night. Scientists still debate how precisely the bird adjusts the tension of its facial feathers in real time. Does it use tiny muscles attached to each feather, or is the adjustment a passive response to changes in blood flow and temperature? We also lack a complete map of the neural pathways that translate the amplified sound into three-dimensional spatial coordinates in the owl's brain. The exact circuitry remains elusive. Another puzzle lies in the limits of the system. How does the owl cope with overlapping sounds from multiple prey or with the acoustic clutter of a rainstorm? Some observations suggest that owls may employ a form of selective attention, but the mechanisms are unknown. Finally, researchers wonder whether other nocturnal birds have evolved similar hidden acoustic adaptations that we have yet to notice. Uncovering these secrets will require innovative field recordings, miniature on-bird sensors, and perhaps new imaging technologies that can peer inside the living skull without harm. As the night deepens and the forest exhales a soft, echoing sigh, the owl remains perched, its facial disc a silent conductor shaping the unseen symphony around it. In that stillness, we glimpse a profound truth. The world is full of hidden mechanisms, elegant and efficient, waiting for curious eyes and ears to notice. The owl's ability to turn a simple arrangement of feathers into a living sonar reminds us that wonder often hides in the most ordinary forms of nature. Each hoot becomes a reminder that we share this planet with creatures that perceive reality in ways we can barely imagine, and that their secrets can inspire new technologies, new stories, and new reverence for the unseen. So when you hear the night's quiet chorus, pause and listen a little deeper. You might just hear the whisper of an ancient, feathered mathematician mapping the darkness, inviting us to marvel at the strange and beautiful tapestry of life. In that moment, the forest itself seems to lean in, honoring the owl's silent mastery, and we are left humbled by the endless ingenuity of evolution.